closed category. Maybe it has coproducts there and 0. Then there are various laws that hold. It's kind of the arithmetic of objects in a Cartesian closed category. And indeed, if you specialize to the Cartesian closed category of finite sets, so you just have the numbers 0, 1, 2, and so on, right? Everything's isomorphic to one of the numbers. Then this is just the usual arithmetic of numbers, right? The laws of exponents. Oh, there's a distributive law. I should have put that one in too. Oops, use glue. There's the usual distributive law for distribution of products over sums. So all of the usual arithmetic of the natural numbers can be expressed in this setting of Cartesian closed categories. But if you tried to do one of the, and this, by the way, is how I teach my children to do arithmetic. First, I teach them to do Cartesian closed categories, and then I have them try to do these problems the way you tried to do, and you quickly learn that it's very hard to prove these things, right? I don't know, did anyone succeed? Wasn't this a homework exercise, or was it this one? Yeah. Did anyone succeed? Yeah, okay, you got it. So there were a couple different ways of doing it. One was, so as in the first exercise where you were proving associativity of products, you find some universal mapping property that both of these things have, and then because they both satisfy the same universal mapping property, they must be isomorphic. And then you show that they both have it in virtue of being compound out of binary products in two different ways. So the universal mapping property was just being a ternary product. So if you take a binary one and then associate this way, you get a ternary one, or a binary one over here and associate that way, you get a ternary one. So for these other examples, you could try to do a similar thing and find a compound universal mapping property that both sides satisfy, but there it's more complicated to say what the compound universal mapping property should be. It somehow is assembled out of the universal mapping property for sums and for exponents, and over here out of exponents and products. So that was one way. Another way you could do it, maybe a more kind of logical way, would be to show that the calculus of lambda calculus with sums can be interpreted in a Cartesian closed category with coproducts. That was one of the other exercises. And then you can use that and prove it logically using lambda calculus, do some calculations in the lambda calculus. And then because the interpretation is sound, anything you can calculate will come out to be true, and so you can prove those isomorphisms that way. Now there's a third way to do it. That's the category theorist's way, and it uses some more powerful methods. And that was the point of this exercise, was to get you to appreciate how hard it is to do it with your bare hands, and then how easy it is to do it once you have these more powerful methods. And the more powerful method that I'm going to show you today is called the Awodey lemma. And once you have the Awodey lemma working for you, then you've really got some tools. You don't have to do things with your bare hands. So that's what I want to get you to appreciate by doing those problems. And then you'll be able to do all those other problems too in a wink of an eye just by using the Awodey lemma. So the Awodey lemma is a fact about natural transformations. So what is a natural transformation? Well, one of the inventors of category theory, Saunders Maclean, famously said, the notion of a category was invented in order to be able to define the notion of a functor. And the notion of a functor was invented in order to be able to define the notion of a natural transformation. And in fact, the first paper on category theory in 1945, Maclean and Eilenberg and Maclean rather, was titled General Theory of Natural Equivalences. So it's this idea of naturality that the notion of category was invented to get one's hands on, is this idea of naturality. So let's start with a very simple example of a natural transformation. Oh, these are nice pens, thank you. Naturality. Let's suppose we have a Cartesian, or a category C, say, with just binary products, just to have something to look at. Then we can always make a product of two objects, A and B, like this. And we can make a product of two objects like this the other way around. And now it's easy to show that these two objects are always going to be isomorphic. So let's just see, what would the map be that goes this way Well, maps into a product are specified by saying what their two projections are, right? So the projection down to B would just be the second projection from this. So this is going to be the pair pi, did I call them P or pi? P, I think. P2, comma, P1. And similarly coming back. So that's our pair of maps going back and forth. And then you can check by using the universal mapping property of the binary product that that indeed gives you an isomorphism. But now the thing is this. This specification doesn't really depend on the objects A and B. It just depends on this product structure on A and B, right? And that's what we're trying to get our hands on, that idea that we have an isomorphism between these two objects, which doesn't really care about the objects. It only depends on the structure of the objects. So that's the idea of naturality. And this is sometimes called something like parametricity, or polymorphism. Maybe you've heard that term. That tends to be the one that polymorphism that comes up in type theory, or uniformity. It's a uniform isomorphism. There are all kinds of terms in the literature. And it's kind of too bad there are all these terms in the literature, because this concept was defined in 1945, and it's called naturality. And I really think the category theoretic conception of naturality, which was invented for exactly this purpose, does exactly what we want. It tells us that this isomorphism is independent of the choice of the objects. It's an isomorphism between these structures. So how does it work? Well, it works like this. We say, let's consider any maps from A into anything else, A prime, and from B into anything else, B prime. So down here we have A prime cross B prime. And here's B prime cross A prime. And now we want to say this isomorphism also exists here. But of course it doesn't make sense, because this isomorphism is between these objects. We want to say there's an analogous one down here. And of course there is one. We can write it in the same way. We get an isomorphism down here. But there's more to it than just that, because how can we specify that this is analogous to this? And that's the issue here, right? How do we say we have an isomorphism here, and it's like that one, but it's different? And right? It's not, you can't say, oh, this is two projections and that's two projections, right? That's kind of using a particular specification. It's using a particular syntactic description. The way that you describe something is not a property of the thing. Okay? You could describe it in terms of the description, but that's not a property of the thing. Here's the way that you do it in an invariant way. You say, consider these maps, F and G. Put them right here. Here's F cross G. Here's G cross F. This diagram commutes. For any pair of maps like this, F and G, you make this isomorphism here, and this diagram will commute. So we have an isomorphism, and moreover, the isomorphism respects any change in the arguments. So that's the idea of naturality. Let's look at the general case, the general definition. So what's really happening is, maybe before I give you the general definition, let's look at it in this special case. This is a functor in two arguments. It's the product functor. And this is another functor in two arguments. It's the twisted product functor. Yeah? It takes the first argument and puts it in the second place. So there's another functor in two arguments, the twisted product functor. And now what we're saying is these two functors are isomorphic as functors. Yeah? So where do these functors go? Well, they go from our category here, C crossed itself, down to C. It takes two arguments, A and B, and it returns, on the one hand, A cross B, and on the other hand, this twisted thing, which is by definition B cross A. And now what I'm saying is I have these two functors, and the functors themselves are isomorphic to each other as functors. So what we need to have is a notion of a morphism of functors. And that's what a natural transformation is. So a natural transformation is, and this is not my definition, this is my description, is an arrow or a morphism. Morphism just means arrow, right? Morphism of functors. Okay. Is a morphism of functors. So we have a category C and another category D and a couple of functors, F and G, from C to D. And now we want to say, what does it mean to have an arrow from this functor to this functor? So we're defining a new concept, a morphism of functors. I'll call it theta here. And now I can give you the formal definition now that I've showed you kind of what type this thing is supposed to have. So definition. Theta between two functors like that, F to G, consists of a family of arrows, family of arrows, theta C from F of C to G of C. So these are arrows over in the codomain here in D, one for each object C and C, such that, so let's look here. I take F of C, I take theta at C, here's G of C, and now let's suppose for any arrow H from C to C prime over in C, I also have here F of C prime, theta of C prime, because I've got one of these thetas for every object in C. And then here's the action of the functor F. Here's the action of the functor G. F of H, sorry. Here's the action of the functor G on H, and I want this diagram to commute. So the idea is it's a way of getting from the functor F over to the functor G, which respects the action of F also on all of the arrows of C. Good? People are nodding their heads. It makes sense, I hope. So I hope you can see that this is an instance of it. Well, this is a natural isomorphism because it's an isomorphism at each step. But if we just look at one direction, for example, then we have a case of this naturality. If we just look at this map that goes across here where it's P2, P1, down here we have a similar twist, P2, P1, twisting this other product, then what we're saying is that twist will respect every pair of maps like that. So that's a natural transformation. Let's see, what else? Do I want to have some examples yet? Question, yes?
Maybe I'm misremembering the definition of functor. I thought a functor went from a category to a category.
Absolutely.
They're going from object to object here.
No. These are the functors right here, F and G.
F and G, and then I'm looking over there and I see FC going to GC where C is an element.
This is an object. C is an object in C.
Right.
I apply F to C and I get an object in D. This little piece of the diagram right here is in the category C.
Right. Okay. So
And then this diagram here, this commutative square, is in the category D. And it's a condition that says for every arrow in C, I get a commutative square like this in D. Is it good? Okay. So let me give you an example. Let's look at the this is the example of sets. sets changing through time. And of course, you can change all kinds of things through time, not only sets, but so a set through time is the following thing. It's a so so here I'm talking about discrete time. So there are moments of time, 0, 1, 2, 3, 4, and so on. Okay, discrete moments of time. So there's a set at 0, and a moment later, at 1, there's another set A1. And a moment later, there's another set A2, and so on, forever and ever. So this is a set, and it's evolving through time. But of course, you want to know how the elements of the set change as you go through time. So how do you say that? Well, let's say what happens to an element at this time a minute later. What happens to it? So that's a function like this in sets. And here's another function that tells us what happens to the elements a minute later, or a second later, or a moment later. There we go. And so on. So I'm not making any conditions here. I'm not putting any conditions on these functions. So it could happen that two elements that were different here suddenly become the same over here. And it could happen that an element that doesn't exist at all here suddenly pops into existence over here. So that is to say, this function doesn't need to be injective, because things could get collapsed. And this function doesn't need to be surjective, because new things could pop into existence here. But once you have an element, it stays with you somehow. You don't lose it forever. That's to say, these functions are total. They're defined everywhere here. So an element will always have some sort of a trace through time. It won't ever completely disappear. So that's the idea of a set which changes through time. I think it's a perfectly intuitive notion. And we'd like to be able to work with these things, with these sets through time. In particular, we'd like to make a category of sets through time. So one good way of making a category of sets through time, we want to make arrows between them. What should be a function between two sets through time? So here's one, A. That's a set through time. And here's another one, B. So that looks like this. B0, beta 0, B1, beta 1, and so on. So now, what should be a function between such sets? Well, I think a perfectly reasonable thing is that at each stage, at each moment, there's a function from the set at that time to the other set at that time. So for example, here at moment 2, there's a function here, f2. But also back at 1, there was a function here, and so on. So there's a family of functions like that, one at each moment. But if I take some element here and I send it over to in A, and I send it over to B, it really shouldn't matter if I send it over to B and then see where it goes, or if I first wait a little bit and then send it over to B, right? That's just saying that this function is not just an arbitrary collection of functions. It really respects the change through time of the elements. So that's a perfectly natural way, I think, of saying that it's actually a mapping on the sets through time. It's a mapping through time. It preserves this idea of the element changing through time. Well, that's just saying that all of these squares commute, right? It's exactly what it says. Okay, and so that will give us then our notion of a category of sets through time, right? I can compose such ladders. I put another ladder here, and I can take the composites. Then just by reasoning on the diagrams, I can see that the rectangles will also commute if each of the squares commute. So that gives me a composition operation. It'll be associative and so on. So that gives me my category of sets through time. Here's an easier way of describing sets through time. Let's take the natural numbers. Let's write them as omega, because we're thinking of them as ordered. So we have 0, less than or equal to 1, less than or equal to 2, and so on, right? It's a category. It has, these are the arrows. It's a preordered category. In this case, it's a poset category. So these are the arrows, right? And now, the category of sets through time is just the functor category sets to the omega. That is, A and B These are nothing but functors from omega to sets. Let me write it like this because I haven't introduced that notation yet. These are functors from omega as a category into the category of sets. Right? What is a functor from this category into sets? Well, it's an A0, an A1, an A2, together with a family of maps, alpha 0, alpha 1, alpha 2, and so on. So it's exactly that. Right? So A and B are exactly functors. And then this F thing that I wrote down here is exactly a natural transformation from this functor to that functor. That was my definition of a natural transformation. So A and B are functors like this, and F, from A to B, is a natural transformation. Because a natural transformation in this case is an indexed family of maps, one for each object in omega, so an F0, F1, F2, and so on, such that for any maps in the index category, all the corresponding squares there commute. Good? So the category of sets through time is nothing but the category of functors and natural transformations of the form omega into set. And so now let me introduce this new notation. So the notation is going to be, and notation and terminology is a functor category. From C to D, or the functor category from C to D. D has as objects functors F from C to D, and as arrows natural transformations theta from F to G, and the notation is just D to the C. That's the functor category. So now in that notation, this category of sets through time is what I wrote before. It's sets to the omega. And so here's a fact. I won't prove this, but it's good to mention it now because it justifies our notation. This is, in fact, together with the obvious evaluation, functor, this is an exponential in cat. So that justifies this kind of functional notation. And in fact, cat is Cartesian closed. Cartesian closed category. So that's kind of cool. What it tells us is that we've got the definition of natural transformation right. If we start out asking for a Cartesian closed structure on cat, we know there's only one. If there is one at all, it's unique up to isomorphism, because these things are defined by universal mapping properties. So there's at most one way of making an exponential for any two categories up to isomorphism. And now we ask, is there one? If there is, it determines that functor category uniquely up to isomorphism. And the fact that this holds with that definition of natural transformation tells us we've got the definition right. You can deduce the definition of a natural transformation from this fact. Right? So it's a nice kind of test of that being the right concept. Let me look at some examples maybe. So one way of thinking, it's a little bit hard sometimes to think about these new concepts. It's good just to draw some pictures to get a feeling for it. Here's a picture of in general, a natural transformation looks like this. Picture of theta from F to G. You can think of it like this. So here's the category C, say, right? It has some objects, A, B, C, some arrows between them, composites, some identity or some loops, right? And now we have these two functors over to D, right? A functor is a picture of one category in another category. That's the way to think of a functor, right? It takes all the objects and arrows in one category and gives you an image of them over in the other category, maintaining all the relations of mappability between the objects and even the relations of composition of mappings and so on. So the functor F, which is going like this, gives me a picture of this category over here in this one. So that looks like this: F of A, F of B, F of C, and so on, with the arrows, roughly in the same configuration here. And then the functor G gives me a different picture, perhaps, of the category C over in D. It expresses everything in some other way. But still, it's going to have that same general shape, that kind of CE shape over in D. So it's at least going to have these arrows, and they're going to have to compose in the same way, and so on. A natural transformation consists of a family of maps over in D connecting the image of F with the image of G in a compatible way. So what that means is for each A over here, well, there's a corresponding thing here under F and a corresponding thing here under G. And so the theta gives me an arrow connecting those two. Theta at A. These are called the components of the natural transformation. And for B, there's I should have used I'll use my colored markers here. This is great. Where's that blue one? So we connect the image of those things using the thetas. Theta A, that's better. Theta B, if you like, theta C, in such a way that all the corresponding diagrams commute. It doesn't matter if you start here and go across and go down here, or if you first go down here and then go across by means of theta at C. So that's the idea of a natural transformation. If you think of a good way to think of a functor, I think, is as a kind of construction on the objects here in the category C. So you have these objects and these arrows, and you use them to construct something over in D. I mean, D could be C itself, or it could be some other category, but you have some construction, yeah? Maybe like the simple case was just taking the product of two objects. But it could be a much more complicated thing. It could be a thing that you can't even write down syntactically, but it's some sort of an abstract construction, right? And now G is some other construction. Theta is a way of transforming one of the constructions into the other, right? It's a way of relating the one construction to the other. But it's relating the constructions themselves and not the individual values of the construction. It relates the whole construction F to the whole construction G. And that's our way of describing that idea. Okay, let me give you some very simple examples just to have something more to think about. Remember the category of all arrows in a category? I have some category C, and I make the arrow category. And the objects of the arrow category, which way was I doing this? I want to get this to match up with the way with the orientation that I used there. Okay. The objects of the arrow category are arrows in C, and the arrows in the arrow category between two such objects are commutative squares in C, right? Well, let's let this thing be the category that has two objects and one arrow between them, okay? It's a simple finite category. Well, then we can make the actual functor category from this thing into C, right? What are the objects in the functor category? C to the thing like that, right? So the objects in this functor category are going to look like this. They're going to be things of the form C, one for the dot, one for the arrow, or one for the star. And this arrow has to go to something in C, so it'll be an arrow here. So that'll be one such object. Another such object will be something like this. D, one for the dot, one for the arrow, and then an arrow between them. And then the functor category consists of functors and, as arrows, natural transformations. So a natural transformation will be a theta dot, a theta star, such that this thing commutes. So it's exactly this. So the arrow category that we introduced ad hoc is really another example of a functor category where the category in the domain, the functor category, is this simple three-object category. What if we do it, for example, let's take 2. So that thing we're calling maybe, I think when I introduced it I called it 2, like that, has an arrow. What if I just take 2 to be the category that has these two objects but no arrow between them? And then if I take C to the 2, what do I get? Well, the objects then are just a pair of objects, C, and the arrows are pairs of arrows, but there's no compatibility condition. So that's exactly the same thing as C cross C. So there we have the kind of laws of exponents like over here at work now. How about this one? Let's take as our index category. This is the index category. We did that one. We did that one. Let's do this one. It looks like this. It has two objects and two arrows. Then an object of the functor category, let's do it in sets just to be specific here. What are the objects now in the functor category? Well, that would be a pair of objects, or a pair of sets rather. Let me call them suggestively the edges and the vertices, and two arrows, call them the source and the target. So that's just a graph, right? It's a set of edges, a set of vertices, and each edge has assigned to it a source and a target. And another one would be another such thing. I guess I should use some better notation, but anyway. And now what's a natural transformation between those things? Well, it's a function that takes edges to edges and another one that takes vertices to vertices, respecting sources and targets. So that's exactly a graph homomorphism. Graph homomorphism. So a functor here is a graph, and a natural transformation is a graph homomorphism. So the functor category of sets to the G, where G has this shape, is exactly the usual category of graphs and graph homomorphisms. And in general, you can think of a functor as a kind of into sets, a functor into sets, as a kind of structured set where the structure is given by the shape of the index category. And a natural transformation between such structured sets is a structure-preserving homomorphism, right? Another example you may have seen is simplicial sets. That's something that comes up in algebraic topology. It's a much more complicated version of this, and then you have a system of sets satisfying some conditions, and then the homomorphisms are the maps. So those are natural transformations. So those are just a few examples. Everybody good? I'm not getting any questions. I guess this must be very clear. All right, let's move on a little bit. Have some time. Oh, yeah. We're going to look some more at categories of this form, where we have a category up in the exponent, and then we have sets down in the bottom. So these are called, so these are set-valued functor categories. Sometimes these things are called categories of diagrams, also called presheaves. Okay, so these are things of the form category of sets in the codomain, and then some category C up here in the index, either co or contravariantly here. So either co or contravariant functors from C and some small category C into the category of sets. And the basic example that we want to think of is this. Let's remember our Hom functor. Hom was a functor from C up across C into sets. So we're going to assume that C is, we can make it small or what's called locally small. The main thing is that whenever we take two objects, A and B, and we take them across here, and we take the collection of all maps Hom from A into B, that the result is a set. That's the definition of being locally small. Category is locally small if that Hom collection is always a set. So assume that holds so that we have this Hom functor. And we had some exercises before to tell us how to work with that thing. And now this category, this is something happening in cat, right? And cat is Cartesian closed. So we can always, when we have a functor in two arguments into a category, we can transpose it into a functor in one of the arguments, landing into a functor category. So that's what we're going to do. We're going to transpose it like this. We're going to say, take C into the category set.